Okay, so today we're going to talk about two topics. Mostly we're going to talk about something called flips, which is a fun sort of combinatorial version of folding, I would say, where you have very discrete operations instead of continuous moves, of linkages, in some sense in the plane, although the moves are kind of going to go out into 3 dimensions briefly. Then the second topic will be about 4 dimensions and higher and how to unfold linkages there, which is a fun result. Mentioned it way back when. But now we have some time to talk about it. There are various ways to motivate flips. They actually go back, they're sort of earlier than most versions of folding. They go back to the 30s. But one way to think about it is, what if I wanted to solve the Carpenter's rule problem, but I had a third dimension to make it easier? So if I have an open chain in the plane, like drawn in here, but I have a third dimension to work in, it's really easy to just pick up that chain and straighten it out. If you've already straightened some of it in a perpendicular plane, if you have universal joints, you can just rotate this up. So this guy ends up being vertical out of the plane. And you just pick up link by link, and you accumulate a straight chain. So this was known much earlier than the Carpenter's rule theorem. Well, much earlier, a whole year earlier, I guess. But it's a lot easier to do this. But what about closed chains? Closed chains are a little bit trickier, and this leads to pocket flipping. So pocket flipping's introduced by Paul Erdős, 1935. Erdős is probably the most famous mathematician of our era. Sadly died several years ago. I never got to meet him, but did a lot of amazing things. And this is in the very early days of his career. As probably a student. He posed this problem, which I will define. So suppose you have some polygon in the plane, and you take what's called the convex hull of the polygon. So the smallest enclosing convex shape that encloses the polygon. So it's going to go here. Some places it might coincide with the polygon. Other places it's going to close off some parts. So that's the convex hull. And then what I'm interested in are these regions in between that are outside the polygon but inside the convex hull. These are called pockets. So here I have just 2 pockets. And Erdős's idea is, what happens if and these edges of the convex hull are called pocket lids. So the idea is, what if I take this pocket and rotate it around the lid out into the third dimension and then plop it back down the other way in the plane? So I can do that for each of these pockets. I pivot around these 2 points through this axis defined by the pocket lid and just rotate the pocket out. If I do that for one pocket, it's guaranteed not to collide with anything up here, because this line extending an edge of the convex hull, the whole polygon is below the line. When I flip the pocket out, it'll be above the line. And that's guaranteed not to intersect anything. So keep doing this. The question that Erdős asked is, will you eventually convexify the polygon in a finite number of steps? That is one of the big things we'll be talking about today. So here's a little example. We start with, just give you a 3D picture. So we start with an orthogonal polygon, which you think of in a plane. And then in this case, there's a single pocket, which is this square. And you pivot that thing around the axis here. And then that's your resulting polygon. Like that, you have 2 more pockets. You flip them. And in this case, we convexify in 3 steps. So that seems good. In case you like reading old mathematics, this is the article in which this appeared. It wasn't an article. It's a section of the American Mathematical Monthly called Advanced Problems. And you ask questions. Presumably you know the answer to them, although we don't know whether Erdős actually had an answer. He says, prove that after a finite number of steps, you get a convex polygon. So he presumably had a proof in mind, but we don't know what it was. let's see, other things here. There's a slight error in the problem, which is that it says, well, it says reflect every pocket, basically. Each of the pockets with respect to the pocket lid, using different terminology here. And if you flip all pockets at once, you actually can get collision. So here's an example. This was discovered a few years later as a follow-up to that question in an answer by Naj. It said, well, if you have this polygon and you flip both of these gray pockets at once, they actually intersect. So you should really do it one at a time. You take the convex hull, take a pocket, flip it out, take the convex hull, take another pocket, flip it out. The pockets change as you flip each one. Another thing to note about this problem is sort of why it's interesting, is the number of flips can be very, very large, even for a quadrilateral, 4 vertices. If I make this point very, very close to this edge, the number of flips here gets arbitrarily large. This is an example where I flip out the gray pocket, then I flip out this gray pocket, then this gray pocket, then this gray pocket. The tighter you draw this example and the longer I make this edge, the more these flips basically go vertical, and it'll just sort of walk up and up and up. And there's actually some circles here. The bigger you make the circles, the closer to vertical they are, and the longer it takes to finish. It will finish in a finite number of moves, but it depends on like our parameter r, the smallest distance versus the largest distance. It doesn't just depend on n. You can't get it bound in terms of n. So in particular, an open problem here is to bound the number of flips in terms of n and r. We've seen a few, we call these pseudo-polynomial bounds, where you get polynomial in n and r. R was maximum distance over minimum distance. But no such bound is known for this problem. Worked on it a few times. Should be possible, but somehow it seems tricky. Maybe it's not true. Explain why it's been so hard. In fact, this problem has a very old history. Erdős was the beginning of it. And then these are all published proofs, I guess on the left-hand side, are all the published proofs of this theorem, at least that we know of. So there was, at the top is Naj. I'll show you more about that in a moment. That was a follow-up in the monthly with a solution. Then Reshetniak came up with the problem independently, and so did Yusupov, both at the same time, more or less, both published in 1957. As far as we know, they're independent of each other. They don't mention each other, so that's in Russia. And then Bing and Kazarinov knew about all of these things. Maybe not Yusupov, apparently. So these are the things that they knew about. Erdős, Naj, Reshetniak. Then Kaluza went and posed the problem in my birth year, and then Wegener solved it, and then Grunbaum finally cleaned this story up and discovered all of these things and wrote a sort of a survey and gave another proof. And then Godfrey Toussaint, who've mentioned a few times, like in the fixed angle chain stuff, he wrote another survey with broader, there's things like flips, which we're also going to talk about today. And so he surveyed that and gave another proof. So as a result, by now we call this the Erdős-Naj theorem. Any planar polygon convexifies after finitely many pocket flips. Because it was posed by Erdős and first solved by Naj, although it keeps getting rediscovered. In fact, we independently came up with it again in 1998. We gave a proof, we found a proof, and then before we published it, thankfully, we found all of these things. So I guess at that point we were here, and that was the source of Gottfried's survey. So, and this was the story for until I started teaching this class 6 years ago. And so I guess this survey was out by then, not the journal version, something like that. And so I thought, okay, I want to present this theorem. It's kind of a classic in the linkage world. It's one of the oldest problems and theorems. So I thought, okay, I'll start with, I'll cover the latest and greatest proof. That should be the simplest, the cleanest. And so I presented it in class. And after I present the proof, I was a little confused about one point. And the student raises his hand. He says, "Is that step 3 really correct?" And it was the part that I was kind of confused about. I was like, well, I'm not sure. I'll get back to you. And so over the weekend, I write to Gottfried and I write to Joe O'Rourke. And it's like, is this right? It seems there's this limiting argument. It doesn't seem quite right. And we figure, okay, maybe it's not quite right. His proof was based on, I think it was based on Grunbaum's and Nage's. Grunbaum's proof is based on Nage's proof. So we went back to Nage's proof. It's conveniently online. I'll show it to you in a moment. And so I presented that proof in the next class. So like, oh, it changes exactly the one step we were confused about. And it has this beautiful, simple geometric argument. It's so cool. 1939. I mean, this is the way mathematics used to be done. It's so cool and great. And then after I present it, same student raises his hand and is like, is that step 3 really correct? And that one definitely is not. And in fact, most of these proofs are wrong. And that was, I guess, I'm not actually sure whether Blaise Gasson was the one, and I'm not sure if this was his final project. We wrote the paper some years later. And most of the proofs are wrong, including the original 1939 proof. So these days, I call it Erdős-Nagy theorem in quotes. The first correct proof is actually Reshetniak's, though it omits a couple of the details. Yusupov's was completely wrong. I mean, not completely wrong, but there's a key step that is wrong, and so it's not a proof. Bing and Kesneranov is probably the nicest, and I'm going to show you that proof today. Their description of it is a little bit terse, but it is right. What's really fascinating, it's in Russian too, so that makes it a little harder to read. What's really fascinating about it is there's one sentence that says, like at the end of the paper, it says, there's a proof by Nage, and they give a reference, talks about this, but the proof is incorrect, and it just stops there. It doesn't say why, but they were right. So somebody knew, but it was forgotten, I guess, since the 60s, and then we rediscovered it in whenever this was, 2000, can't add, 2004, 6 years ago. Let's see. Wagner's proof was wrong, though that's one of the hardest ones to check. Grunbaum's proof, I think, is wrong. At least it omits a key step. And then Gottfried's proof was wrong. And there's another funny story here, which is Gottfried. He's one of the fathers of computational geometry. Many people who do computational geometry today do so because they learned about it from him. So he was there from the beginning. In the beginning of his career, he would read a paper that was about computational geometry as an algorithm for solving some problem like polygon triangulation. And it was before really the field got off the ground and people didn't really have standards of rigor. And so he took an algorithm and he found that it was wrong, and he found a counterexample, and he published a counterexample. And he said this did not make him many friends. So he thought, I thought people were interested in just the truth. But there are more polite ways to point out counterexamples to papers. So he stopped writing counterexample papers. So for many years, he hasn't written one. He used to have a whole series of them. And so I thought, well, Gottfried, will you make an exception if it's about your own proof? And so now he's an author on this. So by now we have correct proofs. There's another proof which is in this paper and a little more general. But and it talks. This is a table from that paper. Cool. So let's prove the theorem, shall we? It's actually not that hard to prove. It's just very hard to prove correctly. I mean, once you get the right ingredients, it's easy to do. There's just a lot of missteps. Actually, before I show you the proof, let me show you the error. Is that true? Yeah, more or less. Okay. So let's say consider an infinite flip sequence. So it's proof by contradiction. We want to prove that it's finite. Suppose you actually succeed in flipping infinitely many times. So you start with some polygon P, which we'll also call P0. And then after one flip, you get P1. And after another flip, you get P2. And then P3. And they go on forever. And what Naj considered was the convex hull. Ci is the convex hull of Pi. Natural enough thing to consider because you flip each pocket outside that convex hull. And then, so his proof looks like this. You're not supposed to read it, but the point is it's about a page long. It's quite short. The top is Erdős' problem again. It shows this example where you can't do multiple flips at once, but then just gives a proof. And there's an argument, I should say. There's one sentence in here. It says each polygon in the sequence P0, C0, P1, C1, P2, C2 contains obviously the foregoing ones in its interior. And so it's about these guys and saying P0 is contained in C0. Well, that's right. C0 is contained in P1. That seems right. And P1 is contained in C. I mean, then it's just, you just keep going. But actually, C0 is not contained in P1. And that was the problem. So you take really any polygon with multiple pockets. It's funny, it's the same issue that when you have multiple pockets, the one that Naj was pointing out. If you flip only one pocket at a time, so the convex hull of the original thing, this is C0, is not contained in the next polygon. It is with respect to that one pocket you flipped, but not with respect to the other pockets. So you don't get containment here. You get containment among the PIs and among the CIs, but not with them interleaved. And that's a key flaw in the proof. So we're going to avoid that issue. And we're even going to, well, at some point we'll use the convex hulls. All right, this proof is going to be basically 5 steps. So, and each one is very easy. So the first claim, so if we look at a vertex and we measure its distance to some fixed point, x, vertices move, but now I'm looking at a point inside the polygon. And I want to look at the distance between them. So I have some polygon. Let's just look at one pocket for now. I take some point x inside the polygon. So here's a point marked x. Notice that as I flip pockets, like I'm going to flip this out here and get something like this, x will stay inside the polygon, right? You always take something that was exterior, you make it interior, and you add even more interior. So the polygon always grows. So if x is right now inside, it will remain inside for the rest of time. So this is actually a well-defined notion inside the polygon. Doesn't depend on time. Doesn't depend on which pi we're looking at. As long as it's in P0, then it will remain in all the others. Okay, so we take this point x, we look at some vertex, like this vertex, distance to x, well, that didn't change. If we look at this vertex, we measure the distance to x. That vertex jumps up here. The distance got bigger. So in general, the claim is the distance never decreases. Could stay the same, but it never decreases. Could stay the same, it could get bigger, but never decreases. So how do I prove that when I do a single flip like this, that this distance increases? It looks intuitive enough, but in fact, one way to think about it is the Voronoi diagram. How many people know the Voronoi diagram? How many don't? Couple. All right. So if I just take this point, and I say, in the plane, which points in the plane are closer to this point versus this one? Well, it's defined by this perpendicular bisector. Everybody below that line is going to be closer to this point compared to that one. Everybody above the line is going to be closer to this point than that one. That is the Voronoi diagram of 2 points. And that perpendicular bisector is exactly the extension of the pocket lid, because we reflect through the pocket lid, and that, of course, that means this is a perpendicular bisector of those 2 points. Therefore, everyone below the line is closer to this than this. In particular, x has to be below the line because the whole polygon was below the line, and x is inside the polygon. So that means this guy x is closer to this point than this point. In other words, this distance is smaller than that one. So proof by Voronoi. All right, so that's step 1, very easy. Step 2, first I'll say what we're going to prove, then I'll say how. Here we get to interesting statements about limits. In general, when you have something that, an infinite sequence of operations, you have something that's moving around an infinite number of discrete times, you worry about what happens in the limit, what happens at infinity. And conceivably, a point could just keep spiraling around, going in a loop, doing weird things, and never really settle down. We claim, though, that in fact every vertex does settle down. There's a unique limiting point that it gets closer and closer to with time. So that is having a unique limit. The way we prove that is using part 1. And we use part 1 3 times from 3 points x, and they must be non-collinear. So we're going to take x1, x2, x3. So 3 points form a non-trivial triangle. And we have some vertex v that we're interested in. We want to show that it converges to some point. And if we look at each of these distances, they only increase. Now, if you're thinking about numbers, and if I have a sequence of numbers and that only increases, there are only two. There's no way that the numbers can go back and forth and loop around because they always increase. So there's 2 options. Either they go off to infinity or they converge to some limit. That's a known thing in calculus. So, and in fact here, they can't get that big because the diameter of the polygon can't get so huge. We're preserving edge lengths. It's a linkage. So the largest the diameter of the polygon could be is like the perimeter over 2. Diameter of the polygon is always at most perimeter over 2. It probably can't get anywhere near that because, in fact, it has to contain the original polygon. This doesn't contain much of anything. But in particular, we know each distance from one of these xi points to v, we know that it never decreases from part 1. And we know it's at most the diameter of the polygon. So it's bounded above by perimeter over 2, which is some fixed thing, it never changes. And therefore, it has a limit, has a unique limit. Just the distances. So the sequence of numbers, the distance from x1 to v as time goes on, has to converge to some limit. Which means that in the limit, v has to lie on a circle centered at x1, and it has to lie in a circle centered at x2, and it has to lie in a circle centered at x3. And because I assumed that x1, x2, x3 were not collinear, these circles will have a unique intersection. 2 circles have 2 points of intersection. 3 generic circles will only have a single point of intersection. And so v must go there in the limit, and so that's a unique point. Okay, so far? So, time for step 3. next thing I'd like to look at are angles. And we're going to use turn angles. I think we've used them recently. Turn angle is that. So here I have 3. The turn angle at this vertex is the amount you have to turn. In general, you might have to turn left or right. So here you're turning left, here you're turning right. Call one of these positive and the other negative. I don't really care which one. Let's say this is positive, this is negative. So you measure this as a positive angle, this is a negative angle. Okay, when you do that, I claim turn angle at every vertex, again, has a unique limit. I switch from approaches to converges, same thing. All right, I'm going to skip some of the details here, but this basically follows from what we have. So we're thinking about what is the turn angle at this vertex, but really it depends on 3 vertices. Call them vi minus 1, vi plus 1. We want to know what the angle is in the limit, so we want to know what the limit of these vertices are. We know by part 2 that those are points in the plane. So by 2, the 3 vertices that define the angle converge to single points. So 3 points total. So we sort of know what they are. We also know, and you can prove this using part 1, that the distances between these 3 vertices never decreases. The interesting part, I mean, the distance between these 2 vertices is fixed, between these 2 vertices is fixed. The distance between these 2 vertices can never decrease, because if you let one of them be x and the other one flips, or vice versa, you know that their distance will increase in each step. With x, this is a special case for x, if x follows one of the vertices. So you have this triangle, you want to measure an angle at it, and you know that none of the worry is if an edge goes to 0, weird things happen, then the angle is not so continuous. But as long as the edges don't get short, and they won't get any shorter than they were before, and then you have sort of a unique, nice limit triangle, and you measure the angle there, and then that is going to be the limit angle. That's it. So it's just we already have it. It's just a matter of checking, because if you have a 0 length edge, there's some angles don't look very nice. But we don't have that, so everything's good. So now we can talk about, there really is a limit polygon. There's vertices there. We can measure angles on that polygon. And that is what the turn angles will converge to. Almost done. Here comes the really cool part. We want to prove that if a vertex moves an infinite number of times, so changes its location an infinite number of times, then in the limit, and now I'm going to use another word for in the limit, which is asymptotically, if I can spell it right. So, I'm going to cheat. I was right. Asymptotically. Maybe I shouldn't have used that word, but there you go. Spelling lesson. Asymptotically. I get a spelling lesson. Excellent. Thanks. Then in the limit, that vertex must be flat. By flat, I mean it has a 0 turn angle. I don't mean this. We call this 180 or plus or minus 180 degree angle. We call this a hairpin. And this we call flat. This is going to be very powerful. The question is, how do we prove it? Answer is very easy. For a vertex to move, it has to be inside a pocket, not just the edges of the pocket lid. But let's say you have some pocket like this. Maybe I should really draw a simpler pocket. Suppose you have a pocket like this. Okay, here's the pocket lid. Then these two vertices move, and they move to something like that. This guy moves up here, this guy moves up here. What happens to the turn angles at those vertices? So let's say we're visiting the polygon in clockwise order. It doesn't matter, just have to be consistent. So I go here, and I need to turn to here. That's a left turn. Up here, I'm going this way, and then I have to turn to going this way. That's a right turn. So every time a vertex flips, or every time a vertex moves, I should say, so it was inside the pocket and it got moved, the turn angle, in fact, the value of the angle stays the same. We don't really care about that. It flips sign. Goes from positive to negative or vice versa. Okay, so what this means is if you measure a turn angle over time, so here's 0, these are the negative values, these are the positive values, it starts at some value, and then every time it moves, it flips sides. And I claim, also we know that it converges to some value, has a unique limit. So I claim it has to look like this and it converges to 0, which would be the flat case. If you tried to converge to something else like this, that's a problem, because if you're going to converge to something other than 0, you're going to have to converge to two different things at once. You're going to have to bounce back and forth. But we already know that's not possible. There's a unique thing you have to approach, not two. And so because you change signs, that thing has to be 0. So if you flip infinitely many times, if you have an infinite number of these edges, you've got to approach 0, which means in the limit, that vertex is flat. Now we're basically done. Let me just show you how to get a contradiction. This is really the heart of the argument. And this is really the step proving almost all of the arguments that I listed before do claim this fact, but many of them have wrong ways to prove it. This turn angle is a really cute way to prove it. And it's how Bing and Kasarinoff did it. Okay, to step 5. Step 5 is called contradiction. How do we get a contradiction? All right, I want to think about the limit situation. Now, yeah. So the limit is going to be some polygon. We don't know. Let's not think too hard about what it looks like. Suppose it's like this. Some vertices are going to be flat in the limit. Some vertices are not. That's all the other ones I drew. Okay, we know that the ones that move infinitely often are these flat guys. Already looking like a problem. The limit presumably is going to be convex, although we don't have to prove that in this argument. In either case, what I'd like to do is think about the convex hull of your shape. Okay, the convex hull has some vertices to it. So like this guy, these guys. So it skips some of the vertices. In fact, it skips all of the flat vertices. If there are flat vertices here, they're not really corners of the convex hull. Convex hull is at most a triangle, or at least maybe a flat thing, although that actually can't happen. But it has at least one vertex, one proper corner that is not a 180 degree, not a flat vertex. So think about those corners. It's got to be at least one of them. They flip finitely many times. That's because we know anything that flips infinitely many times ends up being flat. These guys that are corners of the final convex hull must flip only a finite number of times. So that means after finite time, I take the max of all of those corners of their convergence times. After some finite amount of time, all of these circled points will be in their final position and never move again. That's a problem. So after finite time, now this goes on forever, so there must be a flip at that point. We have all these guys, they're in their static position, and now we do another flip, so like something like this. But that means the convex hull changed. Now this guy becomes a vertex of the convex hull. That's a contradiction. Anything that's going to be on the convex hull should already be there. And so, got a problem. You must actually converge after finite time, namely once all of the corners of the convex hull have converged. We don't really know when that is, we just know it has to be finite, because anybody who's infinite is going to converge to flat, like these guys. So that's it. So a lot of ways to get a contradiction at this point, but this is sort of the easiest that I know. Any questions? Cool.
Do we know what Erdős's motivation for this problem?
Erdős's motivation for this problem? We know nothing. As far as I know, he never wrote about it again. It's just that little paragraph. Presumably a toy problem. It's not clear he was even thinking about folding through 3D. I think the problem just says you reflect through the line. But you can interpret it as folding through 3D. It's nicer from a linkage folding standpoint. Although the thing I'm going to talk about next does not have such an interpretation. But yeah, I don't know why Erdős started this or why the other three groups started it. Just seemed like a natural enough problem. All right. So now we're going to look at a bunch of variations on flips, some of which are better behaved, all of which are finite in the same way. So next one we'll look at is called a flip turn. These were introduced in the 70s by two students, Joss and Shannon. I forget where they were students. They never published their paper, but they gave the example of the quadrilateral that took many, many flips to convexify, arbitrarily many. And then they also introduced this idea of flip turn, where they hope to get a bound on the number of flips purely in terms of n. So for regular Erdős pocket flips, we know you cannot get a bound in terms of n. Flip turns, you can. So what's a flip turn? I should draw a relatively simple example. So flip would correspond to this reflection, right? Something like that. We're not going to do reflection. Instead, we're going to do rotation. So here's the pocket lid. I'm going to take the midpoint of the pocket lid and rotate this subchain around that midpoint by 180 degrees. Should be like that. So in fact, this edge will be parallel to this one, this edge will be parallel to this one, and this edge should be parallel to this one, more or less. Okay, so you see the 180 degree rotation. It's kind of like, it's not really a linkage operation. You detach here and here, and then you rotate it around and reattach. I think some people call this flips with a very low ceiling. So you pick it up, you turn it around, and then you can reattach. Okay, it's a discrete operation, not exactly folding. But what's nice about it is it preserves all the edge directions, even if you look at the order in which you visit them. So I come here, normally I'd visit in that direction. Now I visit the same edge in this direction, exactly the same direction. The directions of edges are preserved. What's changed is the order. There used to be this guy 1, 2, 3, and now it's 3, 2, 1. So you reverse a substring. You still have the property that you don't introduce self-intersection. You can't think of it in the middle of this operation, but at the end, this is outside the convex hull again, so it won't intersect any of the rest. Okay? But in particular, you get that there are at most n factorial configurations that you could possibly reach, one for every permutation of the edges. And it's easy to show that you can never revisit an old configuration because your polygons are always getting bigger. So this implies there will be at most n factorial moves, flip turns, before you convexify. And that's quite different from flips. Flips could be arbitrarily large even when n is 4. Here, for n equals 4, you actually get a reasonable bound on the number of flip turns. But this seemed rather large, and this is in the 70s. Several years later, first paper was in 2000, then another one in 2002, proved that, in fact, it's order n squared. And it's tight. There's an example where no matter what you do, you need quadratically many flip turns to get there. So I want to show you how those proofs work. There's some other fun results. I'll just mention them. With flips, you have in both flips and flip turns, you have a choice of which pocket do I flip first. With flips, if you make different choices, you get different polygons, possibly even different numbers of operations. With flip turns, you always get the same polygon. It won't even be translated. It's exactly the same polygon in the same place, no matter which sequence you do. But the number of flip turns it takes to get there might be different. It's sort of like sorting, because your goal is actually to convexify. If you think of the edge directions as like angles relative to the x-axis, you're actually sorting those numbers. And so you're sorting numbers by flipping subsequences. There's different sorting algorithms, so there's different flip turn algorithms, and they have different numbers of operations.
What if you have two parallel edges?
Two parallel edges, yeah, it's like having two equal numbers in a sequence. You could flip them or not, and you don't care. Still, the final shape will be unique, but the labeling of the edges won't be unique. Yeah. I guess when I say shape, I'm ignoring the flat vertices, because the locations of the flat vertices will not be determined if there are different edge lengths there. Yeah.
Parallel edges are on opposite sides, as in
Parallel edges on opposite sides, those have different directions, and they will be properly sorted. So they will be guaranteed to be something like that.
But can't the kind of orientation of an edge change in a flip?
No, an orientation of an edge never changes in a flip turn.
Right.
Yeah. Yeah, it's pretty cool. We knew it was cool for quite a while before we knew the bound, but then eventually we could use all these nice facts to get it bound. One other result we know is that it's NP-hard. If you want to find the sequence of flip turns that maximizes the number of moves you get to make, that's NP-hard. But the more natural question is, I want to make a sequence of flip turns that minimizes the number of moves I make before I'm convex. That we don't know, whether it's polynomial or NP-hard. So that's open problem. And now we can go on to actual bounds. To start out, I want to look at a simpler case. We'll sort of motivate the general case, which is orthogonal polygons. And for orthogonal polygons, you can prove that it's actually a linear number of flip turns. In fact, less than n. And when I say bounds like this, I mean no matter which flip turn sequence you make, no matter how you make your choices, you convexify, in this case, less than n flip turns. So orthogonal polygons, of course, are something like this. And for orthogonal polygons, I'm going to distinguish two types of flip turns. One, let me make this a little less symmetric. One kind of flip turn, the pocket lid is not orthogonal. We'll call those diagonal flip turns. In this case, you'll actually get a nice corner. Doesn't matter that these lengths are different. If you were flipping, they would be different, but because you're rotating, you just pop that pocket out. This one, the lid happens to be orthogonal because these two edges are degenerate. But we're going to allow that. In that case, you'd get something like this. So orthogonal pocket flip turns versus diagonal flip turns. So first thing we're going to do is look at orthogonal flip turns and bound them. We claim that no matter what you do, they kill two brackets. bracket. Bracket is this or this in any orientation. So square brackets. So here the polygon could be on the inside, polygon could be on the outside. I mean two turns in the same direction, basically, consecutive. They can overlap. So if I have something like this, there's two brackets here. There's one bracket there, another bracket there. Okay. This is basically a case analysis. I'll show you some examples. If I have a polygon like this, and I flip turn this out, there used to be a bracket here. And now on the top there isn't. It goes right then left. And there used to be a bracket here, and now there isn't. You go left then right. Okay, but there's sort of three cases to worry about. And this one, a little tricky. So the left part is about the same. This bracket gets destroyed. This bracket also gets destroyed, but something else happens. Let's see, this bracket gets destroyed. That's kind of nice. But this one becomes a bracket. This one was not a bracket before, and now it is. So that's a little annoying. But you add it up, there's still, in net, you lost 2. And then there's one more case, just like this. I mean, I'm just making cases about whether here I turn left or right. So in this case, this bracket gets destroyed, this bracket gets destroyed, and these guys don't change. They weren't brackets before or after. So and you have to do a little more work to show that number of brackets never increases in this world. And every time you do an orthogonal flip turn, you kill 2 of them. Therefore, there are at most n over 2 orthogonal flip turns. Because they're at most n over 2 brackets. You have to think about that to prove it, but it is true. In fact, one second. I think I must be wrong then if there's going to be only at most n over 2. And it's not a big deal. It's n versus n over 2. But to get n over 2, the worry is something like a spiral polygon. And a spiral polygon should have about n brackets the way I've defined it. But if you only count interior brackets, not these exterior brackets, then there will only be n over 2 of these. So every time you twist one way, you have to untwist back. So I have to check the paper to see. I think we must define them to be interior brackets, the polygon on the inside. But it's not a big deal either way. It's just a factor of 2 difference. But I'm not about to do the case analysis for both versions all at once. OK, but we still haven't worried about the diagonal flip turns. Diagonal flip turns turn out to be easier. So here's a diagonal flip turn. This edge ends up going here, and this edge ends up going here. So in fact, you obliterate these vertices. They become flat. So diagonal flip turns flatten 2 vertices. And once a vertex is flattened, basically you can never see it again. It's gone forever. You've taken 2 equal slopes, put them next to each other. So that means there's at most actually less than n over 2 of these, because you can't get rid of all the vertices. In the end, the final shape will be a rectangle. And so there are 4 vertices you don't get to kill. So you add those up, it's less than n. And that's the orthogonal case. So that's pretty easy. Let's generalize a little. So, oh, I have an open question too. If you really want to get the right constant, it's possible you could get less than 1 times n. Something like 5/6 n is the worst example we know. It'd be interesting if either you find an example that requires almost n flip turns, n minus some constant, or you get a better upper bound and show that it's 5/6 n or something bigger than that. All right. Now we go to general polygons. I think I'll just give a sketch of how this works. But pretty much everything works the same, except we use our good friend turn angle, but a discrete version of turn angle. Now, what could this possibly mean? Well, orthogonal shapes are really easy to think about because there's only 4 edge directions. There's the 2 horizontal ones, the 2 vertical ones. Let's not worry about edge directions, although that's really what is happening with the sorting. Let's just think about slopes. So there's horizontal slope and vertical slope. Let's suppose I have a polygon now with S slopes. If S is 2, we already solved it. You can, it's not totally obvious. We solved 2 particular slopes. S equals 2 could be you have some skewed shapes like this. Yeah. But in general, you have some number of slopes. It could be n, but let's distinguish how many there are. And then to measure a turn angle, I have some edge at some slope, and then the next edge is at some other slope. In between, I just want to make note of how many slopes there are in between. So there was the slope I started with, and then some number of other slopes that appear somewhere in the polygon in between. I'm going to say the turn angle here is 3 because there are 3 slopes there. Okay, it's always going to be an integer. That's discrete turn angle. It's a weird notion. This is the only paper I know that uses it. The ones that talk about flip turns. Okay, but it's some number for each of the guys, and I claim basically it keeps decreasing, and that's what makes my life good. It lets me bound the number of steps. So there are 2 kinds of flip turns. There's the, I'll say, non-degenerate ones, which are like the diagonal ones from before. So non-degenerate ones, these 2 edges that bound the pocket, so here's the pocket, these 2 edges are not parallel, so one of them turns a little bit. So non-degenerate case where I get, something like this after I flip. If you count it, the total discrete turn angle goes down by at least 2 in all cases. So for example, let's say I have these slopes, so 45 degrees. So the discrete turn angle here is, and I'm not going to worry about signs here, this is 2. I have to go 2 steps in order to get to here. And over here, it's sharp. Is that it's a 90 degree angle, let's say. So I have to go 1. I can't count. It's just 2 again. 90 degree angles are discrete turn angle of 2. But now, after I flip, this is only a discrete turn angle of 1, and this is a discrete turn angle of 1. So in aggregate, I went down by 2. In general, in total, you'll go down by 2. And you never, I'd like to say that it never increases. Sadly, it does. This is where things get a little more interesting. In the non-degenerate case, it always goes down by 2. Life is good. But we have these pesky degenerate cases. And for that, we needed brackets up here. We're going to generalize the notion of brackets. a bracket is now going to be something like this. Make it a little different. So the turn angles here don't have to be the same, but they have to have the same sign. Here I'm turning right twice. And I don't know whether the polygon has to be on the inside or the outside. That will only affect things by a factor of 2, maybe. Got to get it right, but I don't know which way it is offhand. So claim is degenerate flip turns still decrease the number of brackets by at least 2. Same analysis as before, really. We didn't use that it was orthogonal. We were just caring about whether you next turned right or next turned left. So same argument works to prove this fact. The annoying thing is that they also increase the sum of the discrete turn angles. Do I have an example? I don't have an example. We can try to make one. So here we get this. So here the turn angle, it's basically the reverse of the previous situation. Here the discrete turn angle was 1, now it's 2. And here it was 2. 2 to go there. Now it's 1. I didn't succeed. But it can be done. The claim, though, is the number of discrete turn angles is at most, or the total change is by at most 2. So we take a step backward in the sum of turn angles, but number of brackets we make monotone progress on. You can check that the non-degenerate ones still don't create new brackets. They don't decrease it, but at least they don't create new brackets. So if we think of brackets as the highest priority, and then after minimizing brackets, you then try to minimize sum of discrete turn angle, together this will eventually say that it's finite, and you might get some n cubed bound if you don't do that carefully. You can be a little more clever and say, the quantity I care about, I'll call it phi. People who know amortization should recognize that. So we have, on the one hand, total discrete turn angle. And on the other hand, we have the number of brackets. I'm going to multiply the number of brackets by a half and add those two quantities together. And with this weighting, you can show that every flip turn you do decreases this thing by at least 1, hopefully, if I did it right. And so now you know this quantity goes down by 1 in every step. It starts out at most something like n times s. And at the end, it's got to be at least 0, and it decreases every step. So the number of steps is at most n times s. So in particular, if you have n slopes, this is n squared. If you have some smaller number of slopes, it's better. Like 2 slopes, you get n again. That's flip turns. Any questions about them? I think that's all the proofs we'll do today. So now we get to go to more fun operations. Next one is called deflation. Deflation is the inverse of a flip. Regular old Erdős flips. So Erdős flips look here, they're the regular reflection. Something like that. So going from this polygon to that polygon is a flip. Going from this polygon to that polygon is a deflation. Just the opposite. Now, we know that flips eventually stop in finite time. Wegener introduced deflation, and he conjectured that if you can only deflate a finite number of times. But it's not true. Whoops. Yeah, it's not true. I'll show you this. So this is a quadrilateral in the top left. It has specific edge lengths, 6, 4, 3, 5. And if you deflate, you get a non-convex quad. And then you deflate again, and then you deflate again. Sorry, I guess that thing is this polygon But you deflate like this, you get that polygon. You deflate again, and it gets so hard to draw because all the edges are on top of each other. But this will actually never finish. You can keep deflating. In the limit, it will be flat. And you can go on forever. You never actually get to flat in a finite number of steps. The angles get divided in 2 or so every time. Just give you an idea why that polygon works and what quadrilaterals actually work. If you want a quadrilateral to lie flat in the end, you measure out the lengths. So let me draw it convex to get started. We have A, B, C, and D. So here we go right A, then we go left B, then we go right C, then we go left D. We want those to close up in the end. So the alternating sum, this is like Kawasaki's theorem, is 0. In other words, A plus C should equal B plus D. Okay, in this case, it doesn't equal 180 because there's no angles here. These are lengths. But it's just like Kawasaki. And so if you check those edge lengths, 6 plus 3 is 9, 4 plus 5 is 9. That's what allows this example to work. It turns out every polygon where there are no duplicate edge lengths, if you had parallelogram, this wouldn't work. But as long as you have unique every edge length is different, and you have this property, then your quadrilateral will deflate infinitely. It's kind of cool. No matter how you do it. Quadrilaterals, it's unique. There's a bunch of open problems here about larger polygons. So one paper we wrote is called Deflating the Pentagon. And it's about deflating pentagons. And we proved that if you take any pentagon that has no flat vertices are cheating because they're like, you actually have a smaller polygon. If you have a pentagon with no flat vertices, it always deflates after finitely many steps. It's good news if you want to deflate a pentagon. If you won't, whereas quadrilaterals, it can take forever. Pentagons, it doesn't. Hexagons, yeah, you can make a hexagon by joining together 2 of these. But what's open is there a hexagon with no flat vertices that no matter how you deflate it, it always ends up flat, like the quadrilateral does. So there are examples that no matter how you deflate it, it does take forever, but they don't converge to something infinite. And that's open for hexagons on anything larger than 5. Pentagons are special. There's a brand new result this year. It says at least if you take some sequence of deflations, at least you have a unique limit polygon, which is what we proved for the flip case. So that generalizes to deflations. But that's about all we know. In general, characterizing these polygons that deflate infinitely much is an open problem. All right, I skipped over one slide here. This is another generalization. If you look at regular flips, Erdős flips, but when your original polygon is self-intersecting, it's an ugly mess over there, you can still define a flip. You can draw that, take the convex hull, take a pocket of the convex hull, flip that mess out, repeat, repeat. Eventually, it turns out, you'll get simple, and eventually you get convex. And in a generalization of the proof that I showed you, you can establish this. You just have to generalize the notion of turn angle. So it's not too hard. It'll still be finitely many steps. The next topic is POPs. POPs are very simple. Instead of this global notion of taking a convex hull and flipping a pocket outside the convex hull, we're just going to look at 2 edges. Let me make it not so symmetric. Polygon does whatever it does out here. I don't know. This could be inside the convex hull. Who knows what? I take those 2 edges. I take the lid that they define, and I reflect like that. So I can take any adjacent edges, flip them around the closing triangle, and changes my polygon. Now, it might get self-intersection now. We have to worry about that. In fact, this is an example of a polygon P on the top, where no matter which pop you do, you become self-intersecting. So there's no hope of getting rid of or avoiding self-intersection here. So allow self-intersection. Don't worry about it. Just keep doing pops and until you drop, I guess. there's no notion of finiteness here because you could pop on pop, pop on pop. There's no directionality, so you're not necessarily making progress. But the question still remains: if you're clever and you choose a good sequence of pops and snaps and crackles, can you convexify your polygon? And it turns out this is open for 9 years, 8 years, I guess. And the answer is no. You cannot always convexify. Now, if your polygons are non-degenerate, some generic thing, I think the answer is yes. Never seen full proof of that, but Thurston claims it's true. And Thurston is super smart, so it's almost certainly true. But for degenerate situations, Dumitrescu and Hilscher found this family of examples. So you take, good friends, the x-axis and the y-axis, and you take a polygon that starts, let's say, with a vertex on the x-axis, and it always alternates between x-axis and y-axis. There's a lot of ways to do this. I can go around like this, come back, whatever, but every vertex is on the x or y-axis, and I always alternate between x and y. This is called an alternating polygon. That's a new notion. I haven't heard that before. What's annoying about these is no matter which pop you do, your thing will still be alternating. I drew it non-self-intersecting here, but after I do a pop, like if I pop this vertex, in other words, these two edges, it'll end up like this. So it'll be self-intersecting, but we ignore those. But it's still alternating, because this guy will end up still on the y-axis, just the other side. No matter what you do, you'll remain an alternating polygon. Furthermore, there are no convex alternating polygons, except if n equals 4, then you can do this. But if n is bigger than 4, every alternating polygon is non-convex, and you stay within that family, so you'll never get out by pops. That's a very cool example. Took a long time for people to think about it, to find it. Let's see. All right, there's a whole other topic I wanted to talk about. Like, why am I under time? This time, I'm going to remember to cover my last page of notes. Just to mention briefly, instead of pops, you can define pop turns. It's like the closure of all these different things. It's like a flip turn, but you only look at two edges. So now you'll get this instead of that. This is a pop turn. And pop turns are easier. You can always convexify. We can give an algorithm to always convexify. We can even avoid self-intersection in certain cases. What's neat about, why we really cared about pop turns, because it's a little bit of a weird operation, but it's equivalent to pops if all your edge lengths are the same. So here, I've drawn these edge lengths different. If you have two equal edge lengths, this triangle is nice and isosceles and symmetric. So whether I do a pop or a pop turn, it's like this. So for equilateral polygons, pop turns are the same as pops, and here you get good results. So this kind of bad example could never happen for pop turns, so it can never happen for equilateral polygons. It's kind of neat. That's the end of flips and friends. We now move on to 4 dimensions. I think I have a slide illustrating the 4th dimension. Yeah, there it is. You can all see it, right? Okay, so we now do linkages in 4D. So you may recall that if we're looking at, say, open chains, regular universal joints, open chains in 2 dimensions, Carpenter's rule theorem, they can always be straightened. In 3 dimensions, they can't always be straightened as knitting needles. And in 4 dimensions and higher, they can always be straightened. So let's prove that last fact with some chalk. So we're going to straighten a 4D chain, and then by FedExing, you can turn a 4D chain from any shape to any other shape. Open chain for now, but this is also known for closed chains. It's also known for trees. Closed chains are a little bit more effort, so I won't prove it here. Trees are almost identical. I'll tell you how that works. But key situation is open chain. So you have some open chain in 4 dimensions, really hard to imagine, and we're going to straighten it out without collision. This is a result by Roxana Kochen and Joe O'Rourke from 9 years ago. It precedes the Carpenter's rule theorem. This is easier. So a basic idea is look at the first bar and the second bar and say, well, I want to straighten. Really what I'd like to do is move this bar out so that it is collinear with the first bar is collinear with the second bar. I'll say the first bar extends the second bar. Again, I don't want a hairpin. I want it to be a flat angle, 180 degrees. If I could do that, then and then I can think of this vertex as fused. I'll never move it again. Always treat these guys as a single bar. Then I effectively have a chain with n-1 edges, if I started with n. So by induction, eventually I can straighten everything. So as long as I could do this move to straighten out the first and second bars, I'm done. The question is, can I do that? And most of this argument will sound like it works in 3D, and it better not. It's not possible in 3D. So I want to move this guy from here to here without collision. There are 2 problems. One is that this goal configuration might be obstructed by the rest of the linkage. Maybe the linkage comes around here and it intersects this line segment where I want to go. So it could be my goal. So let's say problem 1 is that the goal configuration for that first bar might be obstructed. Problem 2 is even if it's not obstructed, maybe I can't get there. Can you get there? Problem 1 is easy to deal with, I think even in 3 dimensions. The idea is if your goal is obstructed, just perturb the whole chain, just jiggle it a little bit. It's actually pretty rare that we have these these line segments that form our chain, and this is a line segment goal. So maybe they pierce it at a single point, or maybe if you're really unlucky, they lie along it. Maybe the chain lies along that goal spot, and then leaves. But all of those things will be broken if you just jiggle it a little bit. You'll just fall off the line, or you won't pierce the line, you'll just come really close to it. So problem 1 is actually really easy. And I won't detail how that. You can prove it more carefully without using random perturbation, using a deterministic strategy. But it's really easy, even in 3 dimensions. Problem 2 is the interesting part. Can you get there? So at least I'll guarantee that there's space for the first bar to live extending the second bar. But in 3D, you won't be able to get there. Let me show you why that's true. Why it's not possible in 3D and why it is possible in 4D. So what I want to look at is a sphere centered at the first joint, really, if you exclude the endpoint. And the radius is going to be equal to the length of the first bar. So I draw a sphere like that. Sorry, it's not perfect. Centered there, passing through that point. So the endpoint of the chain will always lie around that sphere if I think of this as pinned to space, 3 space or 4 space. And my goal, I'm starting at one point on the sphere. My goal is to get to another point on the sphere, up here, which would extend that edge, the second bar. So I start at one point, I want to get to another point. The motions I can do are just points on the sphere. I can move anywhere on the sphere I want. Well, except for where these things potentially make obstacles. The rest of the chain could provide obstacles for this bar. I can't collide with it. How do I see that? I just take this chain, which might go all over the place, and project it onto the sphere. Now, in particular, it might be inside the sphere. That's the case I worry about, because that's what could actually hit. If I take this stuff, I project it onto the sphere, I'm going to get some spherical arcs here. And in particular, I need to shift this picture down a little bit. Here's the center. Here's my goal position. Let me move it a little bit. Here's my goal position. In particular, in 3D, I can get an arc like this, an arc like this, and an arc like this. We call this a cage. You might be out here, and your goal is to get there. You can't do it because these obstacles are a little conservative, but you can set it up so that, in particular with knitting needles, so that these are real obstacles, and there's no way to get from here to here. In 4D, this can't happen. Because, and now you have to stretch your imagination a little bit, instead of having, we call this a two-sphere, because the surface is only two-dimensional. It lives in 3 dimensions, but it's a two-dimensional surface. If you go up a dimension, if we live in 4D, then again, this first vertex, the endpoint, moves on a sphere, but now it's a 3-dimensional surface, which lives in 4D. So you have a 3-dimensional surface, and these obstacles, they remain one-dimensional because they are single line segments, individual line segments. So you have this, I can't draw this, but you have a 3-sphere, and now you have one-dimensional arcs. The analog would be you have a 2-sphere, and you have single points that are your obstacles. And now I want to move from here to here without hitting any of the points. That's really easy. Now you can't always go straight, because there might be a point along the way, but you just dive around them. It's the same thing. In 4D, you have this 3-dimensional space. It happens to be a sphere, but don't worry about it. You have these one-dimensional arcs to avoid. You can easily just avoid them, just from the dimensionality gap.
So you would need surfaces instead.
Yeah, if you wanted to lock something, you would need 2-dimensional surfaces in 4D. Yeah. So that's what's going on. To make lock things, you want the dimensionality gap between your space and the objects you're trying to fold to be 2. When it's 3 versus 1, we get locked chains in 3D. If it's 4 versus 2, you could get locked polyhedra in 4D. Yeah. That's how you straighten open chains. For trees, it's the same trick. You just work from the leaves backwards. There's a new operation, which is if you've already sort of straightened out these leaves, you have to be able to fold one against the other. But that's exactly the same argument. Shows you can always do that. You just get arbitrarily close instead of right on top of it. And then you flatten a tree. Closed chains, you need a more sophisticated argument because you can't do it link by link exactly, but it's still possible. And that is our linkages in 4 dimensions. And we have one more lecture on Wednesday, which will be about some fun origami topics. Go back to folding 2-dimensional sheets as you requested, but just in 3 dimensions. Keep it easy.